Hi everybody, Mr. Lee here. In this video, we're going to go over potential due to a point charge, and we're going to focus on this formula that you see in front of you. If you haven't watched the previous video, make sure you do that. It's very important for the concepts of this video. We're going to be doing a pretty intricate problem that does require a little bit more of the math side. I have my notes right here on the side of me, so without further ado, let's begin. All right, let's start off with this formula here. Okay, make sure you have this. Potential or electrical potential is equal to the charge across a voltage difference, or delta V, which is also equal to K Q1 Q2 over R. For the beginning of this problem, we're actually going to only focus on the latter half of the equation, the K Q1 Q2 over R, and we're going to dive exactly what that formula means. Let's begin. All right, so to make sure that we have everything that we need, let's start off with that formula. UE is equal to K Q1 Q2 over R. All right, now in order to solve this problem, or before we even get to the problem, we need to work with a lot of the conceptual ideas first, okay? And this idea of infinity. All right, so let's say we have empty space, right? Space just, well, empty space just being redundant, I guess, where there's nothing around, no charges, nothing. And then all of a sudden, in the this distant corner here, we see a positive charge, boop, magically appear. All right, so what we want to do is we want to move this positive charge to this location right here. And so what we do is with our magical fingers, we grab the charge and we bring it to this location right there. Now, this idea here is the idea of what it means to bring a charge from infinity. Okay, so we say that this distance is infinite away. So when we move this charge from a distance infinity away to a location that we want, we'll just call this location A, we get to say that there is no work done on the charge. And this is a great time to remind yourselves that work is equal to the change in energy. Now you might be thinking, Mr. Lee, what do you mean there is no work that is done to move that charge from infinite away to this location? Well, the reason behind that is in order to move that charge from a distance infinite away to this location, we're not going against or with a field to do this, right? We are in space. There's nothing around. So it's as if instead of bringing that charge from an infinite location to a location there, we just zoomed in on that charge at that spot. Okay, it's the same thing. Nothing was done, right? We're not going against anything. There was no evidence of doing so. All right, so to bring a charge from infinite away in space where there's nothing else around to another location, work is equal to 0. And because work is 0, there was no change in potential energy. So we say in order to do this, this object currently has an electric potential of 0. Okay, and another way to think about this conceptually or with a formula is by going back to our base formula here, okay, where we have KQ1, Q2 over R. There is no Q2, therefore there is no potential. And if you're thinking, well, what about the other formula, Mr. Lee? Q delta V. Remember, there's nothing around, so there is no delta V, right? There is no change in voltage, so our potential is 0. Okay, so that is the first major hurdle that we have to come across. So now let's say we have a charge here at point A. Let's do that in red. Okay, and we'll say that's a positive charge right there. And off in another corner, let's say over here, we see another positive charge. Okay, and we want to move that positive charge right here to point B. Okay, and from here to here, we say it is a infinite distance away. But here, in order to move this new charge to location B, because we are under the influence of this charge here, it will require work to move this charge to point B. So here, the electric potential is not 0, but rather we can figure out using K Q1 Q2 over R. Okay, so in order to move this charge, I'm just going to call it charge B, to location B, work has to be done because we are going against the electric field of A. Okay, now I want to also keep in mind here, now this will get a little messy, and so I'll do this off on the side. This is a little side sketch of what's happening here. So here we have charge A and we have charge B. So what we currently have are two charges, and both of them have E fields. Right? If I were to just do a quick little E field sketch, it will look something like this. Okay, so within this region of space, we have E fields. Now, this is important. This idea is important because what we're about to do is we're about to bring a third charge in from a infinite distance away. Now, let's say we have a third charge that's an infinite distance away. Let's say, I don't know, it's right here. Let's say this is called charge C, and we want to bring charge C right here to location C so that we can place a charge right there. All right, now in order to do this, what we are doing is we're doing work against charge A, or the field produced by charge A, and work against the field produced by charge B, right? And that's the reason why I drew this, because in order to bring a charge, a positive charge here, it's going against these field lines, right? It's going against these E field lines, and so work has to be done to bring this positive charge close to charges A and B. All right, so currently we have three charges. Let's see if I could do a quick sketch of this. Yeah, all right, so we have charges A, B, and C. So A here, B here, and C here, and it's going to create a pretty funky looking field. Let's see if I could draw this appropriately. So we have something that looks like this, right? Yeah, there we go. Okay. Now, as I'm doing this, it is a good habit to practice drawing field lines because you never know where you have to draw field lines. All right, so we have charge A, we have charge B, and we have charge C. And the final part of this problem is we have one more charge. Right? We have charge D, and we're moving charge D from, let's say, all the way out here, and we're moving that charge right there to location D. All right, now conceptually, in order to place a charge right here, let's do that in a different color. In order to move that charge right there, we have to go against the fields of A, we have to go against the fields of B, and we have to go against the field of C in order to place a charge right there. And that requires work. All right, now you're wondering, Mr. Lee, what's even the problem here? Okay, so the reason why I'm going over the setup of this problem, because the setup of the problem actually helps us with the solving of the problem. What we're doing is we're taking four charges and we are locating the charges in a arrangement. Okay, and the arrangement will look something like this. We have a positive charge there, we have a positive charge there, we have a positive charge there, and we have a positive charge there. And with these four positive charges, we create a square. So the question is, in order to create this configuration of charges, okay, what is the electric potential of this four charge system if each of these have a side of a square where your distance is A, and A. Oops. And we will say that each one of these charges has a charge magnitude of Q. Q, Q, and Q. All right. So that's the problem, right? What is the electric potential, or how much work will it require to create this configuration that you see in front of you? And that is our problem. So let's begin. So the first thing I want to make sure that we have is that we know the distance between, let's say, charge 1 and 3, or charges 2 and 4. Wherever there we have a diagonal. And the reason for that is, even though this is a square and the square has all sides of A, if I just want to do a quick little side note here. Okay, so if we have squares of A and A, and A, the diagonal distance will always be A root 2, and that's thanks to our special triangle rules. Okay, all right. now let's actually begin. Now for this one, it will get a little bit messy, but I'm going to use the highlighter to really organize my work. I suggest that you try to find ways to really organize your work. Once you get used to these kinds of problems, it won't require as much setup, but it does require a little work ahead of time. So the first thing I want to really go into is how much potential does it require to move just charge 1? And you know what? I'm not gonna write the e's anymore. So just to move charge 1 from an infinite away and there's no charges there, it'll be 0 joules. All right. So now that we have charge 1 in place, right there, now let's start moving the other charges. In order to move charge 2 from a distance of infinity to its location against charge 1, we can just use the formula KQ1 Q2 all divided by R. Okay, and we did say that these two charges have the same magnitude, and so our formula just becomes KQ squared, and the distance between the two is just A. All right, easy enough. I'm going to highlight that work as well. Let's use green. You'll see why in a bit. All right. Okay, now let's move charge 3 against charge 1. All right, so if we're moving charge 3 against charge 1, remember that charge 3 is a distance of a root 2 away, and so our formula becomes KQ squared. Remember, they have the same charges, all divided by a root 2. And we can also say that in order to move charge 3 against charge 2, because we're moving charge 3 against the fields of 1 and 2, okay, it'll just be KQ squared all divided by, there we go, A. Okay, because the distance between them is A. So what I'm going to do here is I'm going to highlight that in a different color so that we can see why later on. All right, and the last one that we have left is we're moving charge 4 against charges 1, we're moving charge 4 against charge 2, and we're moving charge 4 against charge 3. Okay, so let's just do that in numerical order. We have charge 4 against 1, we have charge, and that'll give us KQ squared over A. We have charge 4 against charge 2. And remember, we have the diagonal there, so that'll be KQ squared over A root 2. We have charge 4 being brought against charge 3. So that is not a diagonal one, but one where the distance between is A. All right. And let's use purple for this one. All right. And so that one will be all for charge 4. Okay, so now we can actually answer the question of how much work does it require to come up with this system here that you see. Let me erase my previous work. All right, so in order to do this, we have to create a formula that says that the total electric charge or the total work to create this configuration is equal to U2 on 1 plus U3 on 1 plus U3 on 2 plus U4 on 1 plus U4 on 2 plus U4 on 3. All right, and because we color coded it before, I will also, let me get rid of all that from the previous video. I will also color code this. We said all the 4s were purple. We said all the 3s were blue. And we said that lone one was green. Okay. So if I were to write it down, right now I'm mainly focusing on the ones that are not diagonal, and that's just going to make my math a little bit easier. And so the not diagonal ones are the ones without the square root. So we have KQ squared over A. U3 on 1 has that square root, so I'm just going to write it as U31 plus U32 is KQ squared over A. U41 is KQ squared over A. U42 has a square root in it, so I'm just going to leave it as U42. And U43 is KQ squared over A. Right, and the reason why I wanted to do this is so that I can just add up all the like terms. And so we get UE is equal to, there's 1, 2, 3, 4 of these. So 4KQ squared over A plus U31 plus U42. Okay, and each one of these is KQ squared over A root 2. KQ squared over A root 2. Can't forget about this one. And when we add up these two like terms, what we end up with is 4KQ squared divided by A plus 2KQ squared over A root 2. All right, and at this point, if you want to simplify it a little bit by factoring out a KQ squared over A, we get 4 plus 2 over the root of 2. And you can say with confidence that that is the total amount of work done to create that square configuration. All right, if you're able to follow along, that is perfect. That's about as hard as it gets for our type of problems. It just takes a little bit of patience, and you just got to make sure that everything is nice and organized, and it does make the end work a lot easier. All right, I'll see you next time. Bye-bye.